One of the things I've done is gone back and looked at my videos, and I compared those against the spreadsheet to make sure it was accurate. And there's quite a few of you who gave thumbs down on my review for this meter. Of course, you know, it's probably like 50-50, the number of thumbs down versus thumbs up. You know, nothing wrong with that, you know. But that did tell me that I think that this is a fairly popular meter. And when I was looking at the spreadsheet, the original test for this meter, it was kind of like the 87V. I didn't run the 87V until after I was completely done with the first round of eliminations. The Fluke 101 was clearly the winner, and then I got my hands on an 87V and ran that at those same levels, and it failed. And unfortunately, then we never really knew where the meter had failed at. Well, the same thing had happened with the UNI-T UT139C. I placed the order for it at the same time when I ordered the rest of the meters, and unfortunately it came in a couple of weeks later. So I had already started the tests, and I was a long way into it by the time the meter ever showed up. I just threw this thing right onto the generator where it was sitting, and of course it didn't survive. So again, we never really knew where this meter failed. So I think for completeness, I think it would be good to at least see kind of how this thing does fare. I'm not going to run it on the old generator. We'll be running it. So I'd be comparing this meter against 5K Wise meters. One of the things I'm still concerned about is the UNI-Ts I've tested have all failed at fairly low voltages. The ones that 5KY provided me had actually been damaged during my piezo grill igniter test. They never saw the maximum DC voltage test or the rectified AC test or any of the transients. They never made it that far. They failed on the very first thing I did. I was actually contemplating whether or not to even run that test because I thought it was kind of pointless that, you know, there wouldn't be a meter that was produced that would actually fail that, and both UNI-Ts did. So I'm kind of a little gun shy about even hitting this thing with a static like that, you know, because I think it might actually take it out. As much as I would kind of hate to break from the way that I'm normally testing the meters, I think in this case we're going to make a special case and maybe start with some real basic tests. Maybe just do the very first level of transient testing and then go back and try the static and see if it'll survive it, and if it does, then maybe go on to the remainder of the tests until it fails. UNI-T UT139C, new. Should be new. Definitely a 139C. Operator's manual. Yeah, I'm not sure if this is a conformance sheet. Maybe it's a warranty card. I don't know. Huh. The manual is all in English, which is good. Leads have a nice feel to them. Again, I'm not a big fan of these types of temperature probes. It looks like the last one. See how it's marked up here for the battery polarity. And you can see how it's also marked in the back cover as well. So we insert the batteries into the back first, I guess. It looks like it powers up fine. Alright, so let's take this thing apart. We'll have a look inside. Let's see, it says 6FF-1, 600 volt, 600 milliamp. No brand. Our 10 amp is a 600 volt TDC 600. You can see here that the fuse clips at least have the latch on the side. I don't care for the metal that they use for any of these, but you know, that's not unique to UNI-T. I think I'm going to lift this out of the case and we'll have a look at the back side. So these three 1206s are your high voltage section. That's probably partly why it fails. And not a lot in this meter, I'll tell you. Typically you'll see a lot more clamps, and certainly the high voltage resistors are going to be in part of it. And just looking at this thing, I can understand why it failed so early. After having to debug that 17B, where it just has a contact type, I can tell you these clips are a lot nicer for troubleshooting. Unfortunately, on the 139, I think once this fails, it's going to be this control IC here that goes out, and there's nothing really I can do to repair this. So let's just go ahead and I'll put this back together and we'll do some basic checkouts with it. No cuts going through the board. You know, again, this thing, it's just destined to break down. I've been watching some different reviews people have done on these, and in one video a guy talks about this being a safe meter. I thought, really? And who are you to say that a meter's safe? Are you some kind of an accredited lab? Wow, it's pretty ballsy, especially with a meter like this. This meter fails. We'll probably hook this up to the new generator with our secondary AC line simulator and just see how it does. Gotta make a big deal about the metal insert there. It's there. I would have saved some cost there and maybe had a little bit better front end for it. You know, like you know, you reach down in here, I don't know how the hell you're going to get that fuse out of there. It's kind of, what's the point? Some of those meters at 5kW it's actually had like a little cloth ribbon that went around the fuse, so you'd have a way to pull that thing out of there. Thought that was a fairly good idea. Now this, I think you're just going to have to work a little screwdriver down in there and pop it. Alright, let's do some basic functional tests on this. Kind of see where we're at with it. When we look at some of the main features of the UNI-T UT139C, it has a temperature probe, it's a true RMS meter, it can read down to microamps, it's got non-contact voltage detection. You know, this current probe here, I could care less about. You know, I can plug a current probe into any meter. That's not a big deal. And this meter currently costs about $47. In that same kind of price range, we have my Centec here. This is the P98674. Again, this is a rebranded Maztec MS8268. And again, it's got the photometer, sound pressure meter, ambient temperature sensor. So it's got quite a few features. Again, about $50 if you use the coupon. Then we have the AmProbe AM510. Again, about $50. Both of these meters are not RMS. And then off to the right here at $80 we have the AmProbe AM530 at 5kW cent. And again, this meter is true RMS. So, you know, immediately you kind of ask yourself, well, if this is $50 and it's a true RMS meter and it's got all these features and it's on par with these two which don't have true RMS, and then we look at the fuses and such that are in this meter and it is true RMS, you're going to have to ask yourself, well, why is this thing cheaper? So the front ends of these meters are actually quite a bit better. This AmProbe AM510 actually beat out more than 10 meters in that first round of testing against this Fluke 101. We look at this meter, the Fluke 101, again it's about $50. It's on par with the rest of these. This meter has no current input, it's got no backlight, it has no millivolt DC selection. You know, this is a no frills meter. but I have yet to damage this meter. I suspect if I tried to, it would be somewhere around where the 107 had failed at. So if you're looking for a meter that's as robust as like this 101 and has features like this 139C and costs like $50, good luck, you know. And so I've been very happy with this BM869S from Bryman. This thing has a lot of features and it's very robust, but the price goes up. You know, this meter is probably now about maybe $220 shipped to the US. You know, I think when I bought it, it was about $230. To me, it's obvious, you know, you're not going to expect a meter like this with all these features to, you know, survive like a meter like this would. It's just not going to happen. And I can pretty much guarantee it's not going to survive as good as what this 510 did, because when I ran this meter originally, it failed very early on in the test, and this went on again to basically finish out. It was the finalist in that first round. Okay, so all 4 meters are connected in parallel right now. And then I'm just using coax with a BNC to banana connector for each one. And then these are tied off to my fluke reference. And currently I'm putting out 1 volt. So again, you can see the Maztec here. It's pretty much dead on. The UNI-T is about a millivolt low. The Amprobe AM510 is about 3 millivolts low. And the AM530 is again 3 places out. This is at 1.019. And again, we can see the 2 very close. Amprobe a little low. This is with 1 millivolt applied. You can see it's 0.9 and 1 millivolt with the Amprobe. You can see with the AM510 now, the price is starting to get us. We can't see that millivolt. You can see we're missing a place on it. If we select the UNI-T down to the millivolt range, we can see it's 1.00. So again, the Maztec is a 2000 count meter, and the UNI-T is a 6000 count meter. And both Amprobes are 4,000 counts. Also, it's interesting on the 510 is you have a separate selection switch for the AC and the DC volts. Where on the AM530, you just have a single location for AC and DC. So you have to select this thing between the 2 modes. And it always powers up on AC. This is with 10 volts applied. So all meters basically fairly close. The Maztec's a little hot, about 20 millivolts high in this range. This is looking at the line frequency, again all roughly 60 hertz. This is 400 hertz, 1 kilohertz, 10 kilohertz, 40 kilohertz. You can see right there the AM510 gives up. This is 104, 105. And it's 105 kilohertz right now. So that's pretty impressive. Let's just take them on up higher. Right there. You can see the Maztec fails. Well, that's the limit of the generator. I'd have to hook this up to an RF source. But we're putting out 15 megahertz right now. Both the UNI-T and the Amprobe are having no problems with this. So next I thought we'd take a look at the continuity feature on the UNI-T. We'll compare that against the AM530. And again, the AM530 is very slow. Boy, the release is very long on this meter. I think what we'll do is go ahead and measure all the parameters for this meter, and we'll collect that data and put it in the spreadsheet. So we'll measure the open circuit voltage. Next we're just measuring the resistance threshold for the short and the open. And again, we're going to measure the max frequency before it skips, or in this case it's probably just going to latch it too long. That's 4 hertz, 3.9, 8. So yeah, 3.1 hertz. And here's the continuity test data we just collected for the UNI-T UT139C. So we can see here the 50% duty cycle. It'll run up to 3.1 Hertz, so it's a little bit slower than the Amprobe AM530. It's faster than the Fluke 17B though. The pulse width detection time is sub 5 milliseconds. That's the limit of what I can measure. The short circuit detection limit is 47 ohms, and it releases at 48 ohms, so yeah, only 1 ohm hysteresis. The open circuit voltage is actually quite high. It's 1 volt versus normally about a half a volt. So if you notice up here, this is the other UNI-T, the UT90A, at 2.6 volts. And at the very top, the highest meter is the Bryman at 2.9 volts. We look at the current, it's on par with the Bryman. It's 300 milliamps. The highest by far is the UNI-T UT90A at 1.15 milliamps, but it's on par with the Bryman at 369 milliamps. One of the things we want to do with this is check the accuracy of some of the other modes. So let's just start with the resistance mode. So this is a 1 ohm resistor here. This is with 50 ohms. This is 100. This is a 1K. This is a 10K. This is a 100K. 1 meg. 10 meg. We have a single diode, 2 diodes, and 3 diodes in series. Let's try nulling it. There we go. 150 picofarad, 1 nanofarad, 0.1 microfarad, 1 microfarad, and 10 microfarad. There we go. That's about right. So accuracy wise, the meter looks pretty good. This next test, you can see I've got out the high voltage supply. This is on page 9 of the manual. It says it's forbidden to input voltage higher than 600 volts RMS despite the possibility of measuring higher voltage, as it may damage the instrument. So I would say that's our upper limit, 600 volts. So I've got the Bryman out here to use as a reference. The 2 meters are just in parallel and attached to the output of the high voltage supply. I've had the Bryman up to 1,000 volts, a little over 1,000 volts actually, DC. No problems at all. Yep, we're right there. Yeah, accuracy wise though, the meter looks pretty good. It's on par with the Bryman. I thought I'd compare the Amprobe AM530 and the 139C for their non-contact voltage detection. So I've just got a lamp cord here and I'm going to move this thing in. Let's just see how close this is before it picks it up. Fair distance actually. Let's try that with the UNI-T here. Wow, that's really sensitive. Let's just try it with the 510 here. It's actually a little more sensitive. Nothing like that UNI-T though. You know, if you were just trying to find wiring through your house, that probably would do a much better job. You know, going through the walls and stuff. I guess you'd have to try it out. This is the part of the video where we're going to start doing some transient testing on the meter. So I've been giving it a lot of thought as far as how to proceed. I think rather than to really break suit, I'm going to go ahead and just run the meter starting with the static test. And again, I'm just using this piezo grill starter here, which you can see. I'll put out a little pulse, but boy, not much. So yeah, and the reason I'm doing this is at least in the area where we live, it gets very dry in the winter, and it's not uncommon for me to draw sparks that size just walking through the house. You know, and I'm not always wearing a wrist strap every time I'm playing around with a multimeter, I can tell you that. So to me, this is a pretty basic test for these meters to survive. So again, my plan will be to give it 5 transients, positive and negative, and then we'll go ahead and functional test it. Okay, that's it. We'll go ahead and check this thing out and see if it still works. Should be roughly 5 volts. It looks fine. About 14. Yep, looks good. We'll have to check the millivolt ranges on the fluke. Let's see here in resistance mode. Here's our 10 meg, 1 meg, 100K, 10K, 1K, 100 ohm, 50 ohm, 1 ohm. Continuity test still works. It's in diode check mode. 1 diode, 2 diodes, 3 diodes. Just looking at the K-type thermocouple. 21, yep, looks good. 60 hertz, that's right. Yep, 50% duty cycle, that's right. I'll go ahead and test this thing in the lower voltage ranges, and we'll see if it works there, and if it does, we'll call it good. Okay, so I just finished testing the meter and all the ranges. Looks good. So just an FYI, this is the 5th UNI-T meter that I've tested. 3 of the meters were tested for ESD, and 2 of those meters failed. And those meters were the ones that 5KY had provided me with, and that was a UT61D and a UT61E. That UNI-T UT90A was actually one of the very first meters I tested, and it passed, along with the Maztecs and every other meter I had available at that time. So this is actually the 2nd UNI-T now that has passed this test. That's pretty good. I'm pretty happy about that. But it also means that we have to go on to the next test. This is a similar test to what I see Dave do, and that's that he'll take the meter and he'll hook it up to a line cord, and where he lives the AC line is at 220. Here it's only 110 volts. Then he'll put the meter through the different modes and see if it has any problems with that. That'll happen to me frequently. They'll have the meter in the wrong mode. It'll be connected, or I want to measure something else, and I'll rotate the meter through that's different positions to get to the mode that I need. I can see that happening with a meter hooked up to the AC line. So again, this transient generator has a step-up transformer, so I'll take the 110 volt line voltage that we use here, and we'll step that up to 220, but then I rectify the signal, and that's what I actually put into the meters. So this is a rectified DC signal. I limit the current. The max the transformer is good for is about 500 milliamps, but I lower it even further with the box itself. So the box is monitoring the current, and if the meter draws an excessive amount, it'll just shut down the output. So before we run the test here, so this is on page 2 of the manual, and you'll see item number 6 here. I don't know if the camera will pick this up, but it says to prevent any damage to the instrument, it is forbidden to change the gear of the range switch-in measurement. Now you know what that means. That means if you've got this thing hooked up and you're taking a measurement and you want to do something else, disconnect it, change the switch, reconnect, and take your measurement. So the company is telling you, don't do this test that I'm about to do. Okay? But you know that's not what's going to happen. People are going to rotate that switch while the thing is live. Unfortunately, the 61D and E had failed the ESD test, so those meters were never subjected to this. I did test the UT90A. That had no problems with it. The 139C I had previous to this, I never subjected to that test. I can say that the only other meter that failed this test, I believe, was one of the Tech Powers. Yeah, sure enough. So if I look back at my notes here, the Tech Power TP2844R was the only meter that I've actually ran through this test that failed. You know, and that's quite a few meters. So hopefully this thing will hold up. Okay, the output of the box now is live. And you can see we are definitely putting out some type of voltage. This is in DC mode right now. Here we're in AC, again it is a rectified signal. Actually surprised I can't pick that up. I wonder how they do their frequency measurement. It may require a zero cross or something. That's all there is to it. So we'll go ahead and functional test it, see if it still works. Okay, it looks good. So it survived the AC plus DC test. So it's cleared the first three tests. That's the ESD, the high voltage DC, and the rectified AC test. So that's pretty good. That's on par with the UT90A. It's also on par with a lot of other meters. The surge testing is next. And I'm going to just start that out low, and we'll just start sweeping it up and see what happens.